Hey everyone, Mr. Fritz here. In this video we're going to talk about line classification. Are lines parallel or intersecting or skew? So let's dive in and talk about some definitions. Right off the bat, if we're talking about parallel lines, this is just like parallel lines that you've seen before. And what we say as our classic definition of parallel lines is that the angle between them is 0 degrees. If I have two parallel lines, they have no point of intersection, and the angle that they make is 0 because this follows the same direction as this one. So the angle between them is 0, and there's no intersection. And if we're talking about three-dimensional space, it's important to think about what three-dimensional parallel lines look like. They're following the same direction. That's why they have an angle of 0. And they don't share a same point. So it doesn't matter if I have two lines that are floating in the air. It doesn't matter where they're oriented, right? So I can have this line here and this line here. I can have this line here and this line here. They're still the same angle. They still have an angle of 0 between the two of them, and they don't intersect. So it doesn't matter how I arrange these things. Intersecting lines, they have an angle between them. And it's kind of given in this picture here at theta. So they cross, they actually intersect, they share a common point. I would add that too. They share a common coordinate. And then finally there's skew lines. Skew lines are a little bit different. They haven't meant anything before in two-dimensional space, because in two-dimensional space you're either parallel or intersecting, but in three-dimensional space I can move them apart from each other. So even though they don't ever touch, they are still considered skew because the angle between them is not 0. So parallel is really special because the lines don't touch and they don't cross over if you were to kind of flatten them out. But skew lines, they don't touch, but they also don't have the same angle, or they don't have the same angle between them. So skew lines, we would say that they are not intersecting but they are not in the same direction. So it's kind of like parallel, however, they are not in the same direction. Parallel have to be the same direction. One thing that to note, though, is they still form an angle when the line is translated. Now, what do I mean by that? If I were to take these two lines that are skew and I were to translate them so that they do fall in the same plane, now they are crossing. Whereas parallel lines, even if they are, let's see, how can I show you this? If parallel lines are still kind of like not in the same plane and I move them in the same plane, they still won't intersect. Whereas skew lines, I can move them in the same plane and then they'll actually intersect. So when we talk about skew lines, we will determine that they're not skew because they don't ever occupy the same position, but we can figure out still the angle that's made between them. So let's take a look at an example. Here we have two lines, and they're both given by these parametric equations, and we want to show that line 1 and line 2 is parallel. So let's just write the vector equations for good measure for line 1 and line 2. So the line xyz is given as -1, 1, and 1 plus s times 2 and -2, 4. And then for line 2, this is given as the position vector xyz is going to equal the initial position 1, 0, 3 plus t times -1, 1, -2. Now if I want to show that these lines are parallel, all I actually need to show is that they're moving in the same direction. Another way of saying that is that the direction vectors are parallel. So I need to look at the direction vectors. So are they parallel? And in fact, hopefully you can kind of already see that they are. they are parallel since if I were to take this vector, -2, or 2, -2, 4, that's my direction vector for line 1, that's going to equal some scalar, I believe that's -2, times the direction vector of my second line. So that just shows that they're parallel directions, which shows that they're parallel lines being formed. So that's showing parallel lines. Pretty straightforward parallel lines. Now, why are they not the same line? Because they have different points where they're starting from. All right, let's take a look at this example here where I have 3 lines, and now I want to do 3 different things. Well, 2 different things. I want to first show that lines 2 and 3 they intersect. Then I want to find the angle between them. And then in part B, I want to show that line 1 and 2 are skew. This is going to take a little bit of room here. So I would advise grabbing an extra piece of paper and if you need it, and let's kind of work this out together. So let's start with part A. First thing I want to do is I want to show where lines 2 and 3 intersect. So here's just to summarize. They intersect, 2 lines intersect if they share the same point and this is not enough, and not parallel. So if 2 things share the same point in space and they're not parallel, then they must be intersecting with each other. So let's take a look at these 2 lines. So line 2, we want to get the x, y, z equations of lines 1 and 2. So let's take line 1. Let me fill this out. This is -1 plus 2s. Oh, I'm sorry. I want to use lines 2 and 3. Line 2 has 1 minus t for my x. I'm grabbing all these equations from up here. The y is going to equal t, and the z is going to equal 3 minus 2t. And then let's grab all the equations for line 3. And that's going to be for the x, it's 1 plus 2u, -1 minus u, and 4 plus 3u. And if these lines intersect, then there's some point where all of these values are equal, where the x value for L2 equals the x value for L3, the y value for L2 equals the y value for L3, and so on and so forth. So what we can do here is we can actually treat this like a system of equations. I see actually I see 3 equations with 2 variables. So I'm going to take 2 of these, and I'm going to solve it like a regular system of equations. So I'm going to rewrite this in standard form. So I'm just going to do a little bit of manipulation. This is negative t minus 2u equals 0. And then my second equation, if I move all of this u over, I get t plus u equals -1. So all I did is just manipulated these lines to come up with these standard form equations. Now I've got these are opposites, so that's kind of nice. Let's add it up. T's will cancel, and I get -u equals -1. So u equals 1. What does that mean? That means that when u equals 1, I am at some intersection point with L2 and L3, or at least that the x value and the y values are the same when u equals 1. So really what I need to do next is I need to actually find what the t value is, because really u is just my scalar value in my L3. So I need to kind of match that up with the scalar value in L2 to kind of match all 3 of those coordinates together. So if I plug this u back into my equation here, we had t plus u equals -1. So that means that t is going to have to equal -2. So now what I'm going to do is, since I have my u value and my t value that should make these 2 lines at the same exact position, we're going to compare just that. So let's take L2 and L3, and we're going to plug in these values that I found. So here's like my check over here. We have to confirm the actual intersection. So for L2, I'm going to take 1 minus -2, just plugging in this t value in this x equation. I don't even write x, y, z here. And I have just t, so this is -2. And then for my z, I've got 3 minus 2 times -2. Now that should equal, when I plug u into these 3 equations for L3, that should all equal the same thing. So let's go back and plug in u. 1 plus 2 times 1, and then -1 minus 1, and then 4 plus 3 times -2. And if I check this, see, this is 1 plus 2, which is 3. This is 3. That's good. They both equal 3. This is -2. This is -2. They both equal -2. That's good. This equals 3 plus 4, and this is 4. So let's see, 3 plus 4 is 7, and this is 4 plus negative 6. Oh, I plugged in the wrong value here. This value should actually be not negative 2. This should be 1. So 4 plus 3, those are both 7. Okay, phew, that was close. So because all three of these check with these u and t values that I found, then this is the point of intersection between lines 2 and 3. So at the point 3, negative 2, 7. Notice this is a coordinate, it's a point. It is not a vector, so I'm writing it using vector or coordinate notation horizontally. So that actually takes care of just the first part of part A. Now let's find the angle between these two things. So I'm actually going to open up a new page here. And if I want to find the angle between these two, I want to find theta. And in order to do that, I really only need to use the direction vectors between those two lines. So for L2, my direction vector was negative 1, 1, negative 2. And for L3, my direction vector is 2, negative 1, 3. So we know how to find the angle between two vectors. We have that formula, cosine of theta equals A dot B over the magnitude of A times the magnitude of B. And so using this formula, let's take the dot product between these two, and let's go in another color here. This is going to be negative 1 times 2 plus 1 times negative 1 minus 2 times 3. That's my dot product all over. This will be the square root of 1 squared plus 1 squared plus 2 squared times the square root of the magnitude of L3, 2 squared plus 1 squared plus 3 squared. Let's bring that up here. That's going to equal, on top, I have negative 9 when I add all these together, over, this becomes the square root of 6 times the square root of 14, which is equal to negative 9 over the square root of 84. That's all equal to cosine of theta. So if I take the inverse cosine, theta should equal the inverse cosine, or the arc cosine of negative 9 over the square root of 84. Punch that into my calculator, and that comes out to be approximately 169 degrees. So that's finding the angle between those two lines that intersect. Moving back to our prompt, we have to now do part B. We want to show that lines 1 and 3 are skew. So actually, once again, I'm going to do this on a blank screen here. So follow along with me on your blank piece of paper or on these notes here. If I want to show that these two lines are skew, let's kind of refer back to what it means to be skew. If these are skew, then they are not parallel and no common point. So once I show that they're not parallel, we know that they are either intersecting or skew. And if they've no common point, then they can't be intersecting. So they must be skew. That's kind of what we're doing here. And so once again, we're comparing two lines. We've got L1 and L3 this time. So let's do what we did before. Let's keep track of the x, y, z parametrics of my two lines. So for L1, I have negative 1 plus 2s. For my y, I've got 1 minus 2s. And for my z, I have 1 plus 4s. And we're going to set that equal to all of the parametric equations for L3. So we're kind of going to suppose that these things might intersect. So we're going to do what we did before, finding the intersection point. And then this is L3. And I've got 1 plus 2u. I've got negative 1 minus u. And I've got 4 plus 3u. So just like what we did before is we're going to kind of suppose that these two things intersect. And so we'll find a point where we have a common xy value using a system of equations just like before. So it's going to look a lot like when we were finding an intersection point, but we'll see where that kind of breaks down. Now I kind of brushed over this, but right away we should be able to prove that these things are not parallel. And if you look at the direction vector, that's going to be given by all the coefficients in front of my parameters. So the direction vector for L1 is 2, -2, 4. And the direction vector for L3 is 2, -1, 3. And hopefully you kind of see right away those are not parallel. So that actually kind of takes care of that right away. So now let's actually solve what this system would be. And I'm going to combine these two equations. And let's make this system as below. 2s minus 2u equals 2. Just rearrange these x parametric equations. Then let's rearrange the y parametric equation so it looks like this. I'm going to add them up. S's will cancel and I get negative u equals 0. So that means that u must equal 0. And then if I solve for s, plug this back in, plug in 0 for s, I come out with an s equals 1. So now, just like we did before, let's check the point of intersection. Let's suppose that these actually do intersect, so let's check it. And at this point, what we've done so far is we've shown that there is a u and an s value that will match up the x and y's, but they have to also match up the z. I can have two, and hopefully that makes sense with skew lines. It kind of looks like they are crossing over between two of my coordinates. So right where my fingers are crossing, they would have a common x and y value, but not a common z value. So right now I've shown that there's a common x and a common y, and I'm trying to prove that there isn't a common z. And the way that we do that is just by plugging in these u and s values for z. And I can do that actually all three of these. We can take x, y, and z, and we can plug in 1 for all of these s's, u for all of these u's. So let's take -1 plus 2 times 1. Let's take 1 minus 2 times 1. Let's take 1 plus 4 times 1. That's plugging in my s, and that should equal all of my L2s, or excuse me, L3s. So that's going to be 1 plus 2 times 0, and -1 minus 0, and then 4 plus 3 times 0. And as I kind of run down the line here, let's see, both of these are equal to 1, so that's good. Both of these are equal to -1, so that's good. Now this one here, this is equal to 5, and this one here is equal to 4. Those are not equal, therefore there is not a z value that actually works when these lines are crossing in the xy positions. So that's what's going on here. I've got an intersection between x and y, but not in z. Therefore, these must be skew. All right, and then if we did want to find the angle, remember we said that even though these angles are skew, if I were to translate them so that they are intersecting, I maintain the direction, but I'm just changing the point, these still would cross and form an angle between them. So I've proven that they are skew. If I wanted to find the angle between them, if I were to smush them together, you do the exact same thing we did before, finding the cosine of theta using the dot product divided by the product of the magnitudes. So that was a whole lot of stuff. So I would encourage you to kind of re-look over this and make sure that this makes sense to you before moving on to the U-try problems. Here I've got two parametric equations for you, or rather two lines made up of parametric equations for you. And I want you to just classify both of these. Are they parallel, are they intersecting, or are they skew? And then I want you to figure out what the measure of the angle is between them if they are intersecting or skew. So pause this video and give these problems a shot. All right, and here is the answers. You don't have a letter C, so don't worry about this. But the first set of lines, they do intersect. And the second set of lines, they don't intersect, but they are skew. And if you were to translate them, this is what the angle would be. So hopefully this made a little bit of sense, and thank you for watching.